right, let's talk about morphology. So linguists say that morphemes are the smallest meaningful units of language. You'll find that in pretty much any introductory textbook on linguistics. So what exactly do we mean by that? Well, to think about this, I want us to attend to a very basic division in language. And that is that all of language is basically a combination of stuff that we've memorized, so just long-term memory representations, plus computations that create bigger expressions from the memorized stuff. So that's a really fundamental distinction that you want to understand as a beginning student, but also even if you've done research for like 30 years, it's always good to come back to this basic picture and kind of ask yourself like, okay, what aspect of this basic division am I really investigating? So let's think about the stuff that we've memorized then. Well, so far we've talked about phonemes. So that's certainly information that no matter kind of what your theoretical disposition is, you have to somehow memorize the phonemic representations of your language, or sort of like what are the boundaries of phonological categories in your language. So that's part of your memory representations of language. We also said sort of like small stuff that we memorize. Then we also have to have memory representations for larger chunks. So for example, when the very first time that you hear an expression like rains, cats, and dogs, you may think that the person is a little off and is saying something kind of crazy. Until you realize that actually that's an idiomatic expression and it's associated with a meaning that isn't transparently computed from the meanings of the parts. So in fact, cats and dogs here just stands for heavily. So rains heavily, you can express that with rains, cats, and dogs. You're not actually talking about cats and dogs. So that relationship is something that you also have to memorize. Okay. But now there's something in between these two extremes. So there's small stuff that we memorize, bigger chunks that also have some type of memory representations associated with them. But what about in between? So let's grab some elements from that larger chunk, rains, cats, and dogs. So cats, for example. In order to figure out what the morphemes of the language are, the question that we basically ask is what are the smallest bits that we can input into the combinatory rules that create complex meaning? So what are the smallest meaning carrying elements that we can input to those combinatory routines? So let's think about the string cat. So we can obviously use the term cat to refer to something in the external world. So I can say, oh, there's a cat, and you can just like, oh, you can map that onto an entity. So clearly that string has a meaning, okay? But the sounds within the string, so the k and the and the ta, you can't really use them referentially except to refer to the sound itself or to the letter itself. So of course I can say like, oh, I like writing a T, but now you're in some sense using T as a word on its own. So cat is a morpheme. The plural suffix also is a meaning-bearing element because it has a clear function in this word. You can attach it to a noun and get a plural meaning. My little dots here are representing the plural meaning. It's a little hard to draw here. And so these are sort of elementary, meaningful building blocks. And therefore, they're elements that we call morphemes. So that's what a morpheme is. But still, why should we care about this? Who cares that these words can be decomposed in this way? Well, the reason to care is that a system that computes with morphemes looks very different from a system that computes with whole words. So those are two fundamentally different kinds of architectures for the language system. So let's look at that a little bit. So the types of theories where the computation is done off of morphemes are usually called decomposition theories. And what that just refers to is that these theories maintain that when you, say, perceive a word, what your brain does is decompose it into the constituent morphemes. So basically your brain wants to strip apart those morphemes and then do computation with those morphemes. So full forms are decomposed into these constituent morphemes. Versus a storage theory that says that what your brain stores is whole words, doesn't really care about the internal morphological structure. So the decomposition theory is the sort of morpheme theory. Storage theory would be the more word level theory. And so you'll see this terminology in the literature, so I'll also use that terminology here. Okay, so let's look at the kind of representational properties of these two types of theories then. Under the decomposition theory, the representations that sit in your brain are something like this. So for example, you would have a representation for the morpheme magnet. So that's just that so-called monomorphemic representation. It just has one morpheme in it. But then your brain also has representations for lots of affixes. So ism, ik, is. Okay, so all of these are just stored representations, and in order for you to try actually produce or perceive words, you have to put these representations together and engage the combinatory side of language. So that was what I had on the right side a couple slides ago. In contrast, in the storage theory or the word theory, we're storing whole words. So you would have words like magnetize stored as a kind of an unanalyzed representation in your brain, magnetic, magnetism, so forth. So these, morphologically complex words would just be stored as kind of unanalyzed units in your brain. So alongside with other words like magnolia, magnificent, I'm showing you kind of a phonological neighborhood here, a bunch of words that start similarly. So under the decomposition theory, in order to actually generate a word like magnetism, your brain would retrieve the what's called the root morpheme magnet, then combine that with the affix in order to generate that whole word. And that's a kind of combinatory process that wouldn't then be happening under the storage theory. Okay, so very different ways that the language system could work. Okay, so of course we want to know which of these theories is sort of a better description of what we actually do. So how could we investigate that? Well, it turns out that in these two different types of models, the words of the language relate to each other via different types of similarity relations. Okay, so the relationships between different words to each other are different in the two types of models. I'm going to walk through that a little bit now. And the reason that matters is because similarity relations determine priming effects. And if similarity relations are different in two different theories, then that gives us an opportunity to test those theories with priming experiments. So that's kind of where we're going. So let's look at the decomposition theory first. So here I have the root morpheme magnet and three different morphological derivations that include that root morpheme. And so crucially here, all of these words, so all of these are words of English, but under this theory, they all contain the same bit. Okay, so they all contain the morpheme magnet. So there's something really fundamental that unites them. Okay, so all of them contain the same morpheme magnet. And so for that reason, they all relate to each other via identity. Of course, they're not exactly the same word because the morphologically complex words have an element that the root does not have, but they all share this one computational unit. Okay, so something, if you say magnet and then you say magnetism, there's something that you're repeating. You're retrieving the same element from your lexicon twice. And that's really crucial and useful because it turns out that repetition is a very robust process for our brain. So when we do exactly the same thing twice or retrieve exactly the same representation twice, it's a lot easier to do it the second time around. And so under this kind of a theory, any prime target combination of these words that I'm showing you here should elicit some form of repetition priming, like you're doing the same thing twice. Okay, and that's something that we can actually measure quite nicely. So that's kind of a crucial prediction of the decomposition theory. So we go from one morphological derivative to another one, you're repeating something, you're retrieving the same unit twice. So that should have kind of a special effect on the brain. And so now that's the thing that is not true of the storage theory, okay? So here's our, our representations under the storage theory: magnetized, magnetic, magnet, magnetism. All of these words are similar in sound. So all of the words that I'm showing here are similar in sound, so including magnolia, magnificent, they all are part of the same kind of sound similarity neighborhood, phonological neighborhood. But then, of course, and so because of that, the words that are similar in sound, they should compete with each other in recognition. So if you start hearing something like magnet, you should get kind of a competition effect between all of these words that possibly could fit that representation. So we know that words that are similar to each other but not identical, they usually compete with each other in recognition. And so some of these words are also similar in meaning, okay? And the words that are similar in meaning in this example are exactly the ones that in the previous theory were morphologically related, as in containing the same morpheme. But now under the word theory or the storage theory, there's no such thing as a morpheme. So here we're just looking at the word level relations between these representations. And so the usual prediction would be that, well, if two words are semantically similar but not the same, they you get semantic priming. So one word will kind of activate the other word, and then you might get a facilitatory effect. And so specifically the kind of morphologically related set is the semantically related set in this theory. And so crucially, none of these words relate to each other via identity. And so any priming effect then between two members of the morphological family, which in this theory is not a real thing, should be explainable in terms of sound and meaning similarity alone. So as long as we compute the similarity relationships between the words, no reference to identity or anything like repetition, because that's not what would be happening, you should be able to explain the priming data. So that's the core prediction. So the upshot here is that a morpheme lexicon and a word lexicon contain different similarity relations. And for that reason, they make different predictions about priming. And it's those predictions that we'll be testing next.